I want us to understand this in general terms and not be so, not couple that with RPC. In real life, the trade journals, the way they use these two verbs, client server, it is always linked to RPC. But that is a misuse of the word. So let's look at one example of how you may take something like a monitor and make a client server implementation of this, and thereby also try and understand the typical assumptions that we make regarding client servers. So first, let's everybody clear on this notation here? This is monitors. So the procedures that are inside are invocable one at a time exclusively, and it has the condition variable. In this case, the condition variable is free, and as you know, you're allowed to do rate and signal on condition variables. Okay. So this is what we are about to implement as a client-server solution. So here is the implementation of this. There's a minor typo in your book. Okay, now let's look at, again, we are pretending that we know the total number of clients. That part of it is realistic, but that is essentially material for us. So whenever you are interested in acquiring this resource, which is what monitors effectively are, you send this particular request on the request channel. As you can see above, request channel is a triplet, contains some ID of the process, the index, and the kind of operation that you want. It should be one of acquire or release. And finally, the identity of whatever unit you wish to acquire. And as before, it then expects to get an answer on the reply channel. So there is a reply channel for every process. And then it does whatever with this resource that it has acquired. And when it is done with it, it will again send the request, this time the message of release. So from the client's perspective, where it previously did a procedure called acquire, another procedure called release, it would now do these two things to acquire the resource, and this one thing to release it. You understand? So the potential delay is, of course, on receipt. Okay? So, it is always the client process that initiates things. Okay? In general, this is true for any client-server architecture. Whereas the server process, as you can guess from this, must already exist. So before client can do anything, the server, the corresponding server, should have been created and now working properly. And of course, the client somehow has the ability to contact the server. In this case, he is contacting by knowing the particular channel on which we can do a thing. In other words, the client must necessarily know which channel to send something to. Okay, this will later on become a more general problem. And similarly, he knows on what other channel he should await for the answer. In this case, the reply and the ID channel. In this case, we are assuming that the discipline is with the client, that he won't accidentally try to do a receive reply on somebody else's index. And we come to that as a general problem. So here is the allocator now being written as a separate process, separate from the client. Now this is one specific process. From now on we will call such thing as this a server. And a server is typically a non-terminating process. Once it's started, servers don't terminate. And here is the obvious way to recognize that. Here we have an infinite loop. And in the infinite loop, the first thing a typical server will do is await for a certain request. So almost all servers have this part of the structure commonly. They have an infinite loop, then there is a receive at the very top, and when they receive a particular request, then depending on the request they'll do whatever. In this case, we know that there cannot be any other kind of operations, so we could simply write a non-deterministic if. If it is acquired or released, you do the appropriate thing. Fair enough? And the pending is a queue similar to what we have used zero semaphores. So any solution that uses monitors can therefore be done in terms of clients and servers. Is that clear enough? Even though we did it on one example? Yes? No? Because this structure is similar to any other monitor. Here is a typical driver of a device, in this case a disk, written as a server. So in this sense, this device driver receives its request from, let's say, the operating system ultimately, asking it to read a particular sector or a particular track. That it is doing ultimately in here. Access the disk. And then it sends the answer back to the process that asked for it in a certain long buffer. In this case, we are simply calling it results. Okay. Whereas index is the index or the process that made the request. So ultimately, this is where things are being read, but in the rest of the thing, we are trying to accomplish the following. We are trying to do shortest seek time. That is, at any moment, the disk read-write head is on a particular track. And even though it may be the case that the next immediately received request would make this thing move by, say, 20 tracks, you would honor a later request, which would only make it move by 5 tracks. So if it is right now on track 10, the next immediate request is read something from 20, and the following request is read something from 15. It would do the 15 first, and then 20. Okay? And this is simply to avoid the long seek times. If you don't do this, most operating systems will produce miserable performance in the end. This is present in almost all real-life systems, that they will do shortest seek. And to help do that, we have those two queues, left and right in red boxes. The queues are ordered, but they are ordered in reverse direction. Left is ordered as shown in the decreasing way as you move from front. And right is ordered in the increasing way. as before, we have this non-empty, we have this infinite loop, and as long as the request Q is non-empty, we would then receive, let's forget the green loop there for the time being. Let's concentrate on this. So we receive a request from some process whose identity is given by index, whose requests are, read it in this cylinder. Okay, read a particular number. The number of cylinders is given as CYL. Now, head pause is the position of the head at any movement. If the given cylinder is less than or equal to this, then you insert it into that cube. Otherwise, you insert it into the right cube. If they are equal, it doesn't matter where you insert, so there is a non-determinant. You can note that the two Boolean expressions for these statements overlap, which is perfectly okay in our statements. And then, you take a look at these two cubes, left and right, and where you are. And depending on that size, if one of them is empty, well, then there's nothing else for you to do but to go use the other cube. On the other hand, if both of them are non-empty, so we take the element from either left or right, depending on which one is closer to the head pause. Right? Note that to the immediate left, if you take the first item from left, you would have the least one of that. And if you take the last item on right, you would get the other one. So that is why these are conceptually ordered like a trough there. So that the current position, head pause, should typically be in the middle of these two. So you take that number, and that is what becomes the new cylinder, new head position value. And by accessing this, we are now asking you to move that place. Now, what is happening in this loop? Yeah.
A question. Say we start out with no request in the queue, and obviously, so we will wait for a request. When we get a request,
note that n saved is 0.
Right. Okay. So we go to
the receive request.
We receive the request. We insert it in the appropriate queue, whichever
Okay.
one.
Now it is 1.
Right. We go here to the if statement. Is it true then that this process, maybe I guess my question is notational more than anything else, is it true that this process will stay within the bounds of the do true loop for this particular iteration until the access to the disk is complete?
That is correct.
I guess then I don't understand the purpose of having queues, because you're never going to have more.
So it is minimizing. Oh, this access the disk is done by the real device, and this part of it you could schedule differently.
Okay.
You are imagining that while the accessing the disk is happening, nothing is happening within the disk drive. This is usually not the case.
Okay. So for this particular one, the way it's written, while those last two statements are executing, nothing else is happening in the driver?
No. While access the disk is being executed, there can be a lot of requests that it receives.
Okay. And it will queue them?
It will queue them, yeah.
Okay. But is there a notation to handle that then?
Which part? The access the disk?
Yes,
that's why I think
last two cases. To put those last two cases in some sort of a wait until it's done type of thing.
I'm not following the last two cases.
So the last two statements. Right.
Well, actually, only the access the disk is outside this notation. Send is as we have used so far. This part is, as you can see, pseudocode, access the disk.
Right.
Now, while that is happening, we may not have control in this disk driver. In other words, we are not assuming that process switching did not occur there. It could. So concurrent activity could be happening during this quote-unquote access to the disk.
Okay, well that's fine, but it's still waiting until this process is still waiting, whether it's active or not, it's still waiting for the access to get done before it sends a reply. Am I reading that properly?
I mean, that of course it has.
Right. Well then, another request will go to the channel for a request. It'll go into the request channel, but it will never get put into the left-right queue.
If you remember, we are now doing asynchronous send.
Right.
So the request channel can have any number of requests.
Right. Well, the way it's written here.
No. Let's say that whatever time this is. Meanwhile, lots of clients send their requests. They are all present in this request, right? The next time we go in here, we would have received all those requests, right? This is do not empty request.
Okay.
So we would process until the request channel is all processed, or we are at the very beginning. In this case, n saved is 0.
Okay.
I mean, this situation of n saved 0 can happen again and again.
Right.
But it will certainly happen at the very beginning of life. So until we are through with processing all the outstanding requests, we are not trying to do any seeks. But it's also the case that while the physical disk is doing this, access the disk, the disk driver doesn't have to hang doing nothing. I mean, at this point, you could do other activities. Some other process can execute.
I missed that empty request.
Yeah, no, this is the empty on request is a test on this channel to see that there are no outstanding requests that are yet to be received from that. Now, if you, without doing the empty test, if you did a receive and the channel was empty, then you are stuck until you get a message sent on that, right? This is asynchronous method pattern. Chapter 7 in the book he does asynchronous first. 7 is asynchronous, 8 is synchronous. Okay? Now, again, the point of this is not that this is the best possible this driver. It is simply pointing out that a lot of things that we previously think of as special things, like this one would be considered a device driver written using interrupt handling, etc., could be retaught as servers and clients. Now, of course, that there are only 1 to n clients, etc., is unreasonable. But on the other hand, the only unreasonable part is that we are sending the request, the actual answers, back to the specific requester by keeping track of his index. But all processes have a number, and there is a certain way of contacting the process. So that is the abstraction that we have to be willing to see in here. That these end processes are not the only end processes. As long as there's a way to contact the given process, knowing its ID, we are in good shape. Okay? So here is yet another example of a client server. In this example, we are showing the typical disk driver, which is aiming to reduce the total amount of seek time over a period. This next one is an example of a very trivial version of file servers. Okay? Real-life file servers do far more than what this is showing. However, this is a very important concept to understand, this so-called conversational continuity. In the case of file server, let me explain the intuitive idea of conversational continuity. By that we mean the following. If I am simultaneously talking to, say, 2 or 3 people here, having talked to, for a while, Sakal and if I'm talking to Carlos here, when I resume my discussion with Sacco, I should resume from where I left off. That continuity, so far as he and I are concerned, must be maintained. Even though I, as a server, am interacting with a number of clients. In the case of file systems, when a requester says read the next block, I must read the file that he has opened, not any other. And this is not such an obvious thing to accomplish. And on the other hand, this server does that. Again, as before, we have certain fixed number of clients, and we expect the client to behave properly. Again, it is being done here as a matter of discipline. There is no checking involved here. So the client is going to do an open followed by a certain number of reads, and eventually he will close the file. So the operations are read, write, and close, and he should be able to do these operations, read, write, and close, only after having opened the file. So the open file is received in this channel called open, okay? And that channel takes a string argument, string star of arbitrary length, and the second argument is the ID of the client. In this case, client index to J. So he sends that, and that is received here. Okay. As usual, a non-terminating loop for the server, and we receive this. And again, you check if it is successful, etc. Assuming that it is successful, then you send this reply, open reply, on the open reply channel. And that's a channel of n indices. On these, you send some numbers, some number, and then onwards, you are in this loop. You being this file server. Now, how many file servers have we got? N file servers. Note that this is not one file server. You on this? So, this particular file server is now in this do more loop. While it is in the do more loop, its structure again is typical to our servers. It is now willing to receive one of these operations, read, write, and close. But now it is willing to receive these operations on this particular channel, the I channel, I being the file server's number. Okay. So from then onwards, the client should be sending their request on that particular server ID. So what does the client get in return to doing an open? He gets the server ID. Okay. So that is what we are sending here. Note that this I is the index of the file server. So to begin with, we have n file servers unassigned to anybody. Once a client does an open, one of these file server becomes the file server for that particular client. Until that client is finished with his access, this file server is unavailable to other clients. And that is happening by having received this open, we send a corresponding reply, and then the ith file server is now receiving things on this particular ith access channel, where I is the number of the server. Okay. And it becomes available only after the client has done a close operation, at which point more becomes false, and you of course, as usual, send the normal result of these operations. Okay. And now, because of the more becoming false, you're outside the inner loop. Okay? So here is an example of using n file servers, each one given to the client that had opened a particular file. So at any moment there can be n file opens in this system. Now in real life, this is quite typical of what really happens in the end. Even though you may have an interface with one file server, behind this one file server are typically multiple thread systems, each thread doing the equivalent of this. Note that in this case, we are guaranteeing that you are doing read, write, close, and open the file by allowing you to communicate only with a particular server. In this case, the server that opened that particular file. Okay. So here we are not dealing with the actual disk media being distributed. The disk media is in one place, so it's going to place. On the other hand, the client can be wherever because they're only communicating with the file server using sensors. The next example should be a familiar one to you, but we are going to do this in terms of this client-server idea. The example is dining philosophers, and before I do that, let me ask you a bunch of questions. In the standard way that we write this problem, what does that quote-unquote problem illustrate? The dining philosopher's problem. Is that a solution to a particular problem? What does it, why do we use it in the first place? What are the resources in that case? So the typical way that you write, do we solve the problem of allocating the resources? So for example, I have 5 dining philosophers, 1 plate, and 5 forks, each fork in between 2 philosophers. With this setup, how can we solve that problem? And in particular, solve the problem means what? None of the philosophers should starve. Anybody who is hungry should eventually get to eat. And what else? Well, if they have deadlock, then we will violate starvation. What else? What else can cause starvation? A light lock. If each of them is very polite and takes to the next one after you and all 5 of them do this, then we have a deadlocking situation. Then we have a light locking situation. We should be avoiding that. So with that setup of 5 philosophers and 5 forks in between, and all philosophers are equally privileged, there's no way to solve the problem. That problem will either produce a deadlock or a light lock, or in some unfair way, starvation of some philosophers, not all of them. If there's a deadlock, then that group of processes that are in that deadlock are all starved. Similarly with light lock. And it is possible to produce a deadlock containing all of them. Similarly for light lock. So in order to solve the problem, you either make some philosophers special or you introduce something extra. And in the next problem, the something extra that we are introducing are 5 more processes in addition to the 5 philosophers. We call them waiters. Each philosopher essentially has his own waiter. And the waiter has 1 fork each. So we'll change that in a moment. Roughly speaking, in the middle of things, each of them has a fork. And when a philosopher wishes to eat, he asks his waiter to get 2 forks. Okay. And the waiter then communicates with his neighboring waiters and obtains this second fork. Okay. And then he gives these two forks to the philosopher, and the philosopher eventually finishes eating and gives them back to the waiter, and the waiter cleans these forks and then may give it to others. Okay. So far, that is how we intend to make this new solution work. We have 5 dining philosophers as processes. We have 5 waiters as processes. But have we really solved this problem of when can a waiter acquire the extra fork he needs? I haven't explained to you yet how he will do that. Yeah? Sure. And this involves the notion of a dirty fork. And the way we are going to solve the problem is, a fork becomes dirty when, of course, it is being used to eat. And having used and having made a particular fork dirty, that philosopher doesn't get it again until after that fork becomes clean and used by another philosopher. So by doing this, we are avoiding some kind of a conspiracy between any two philosophers to make the philosopher in the middle go hungry all the time. So here is a bunch of processes. At the bottom are the philosophers. And when the philosopher is hungry, he sends this message to his waiter, the iced philosopher sends it to the iced waiter. And the waiter eventually acquires the 2 forks. And he sends you this message. By the way, we are back to chapter 8. I'm doing all time servers that appear in different places. This is synchronous message passing, CSP notation. So we get this eat message when the waiter has acquired 2 forks for you, and the philosopher does some finite amount of eating. So we assume that this terminates, and then we move to saying to the waiter that you are through, and you go back to the thing. So the philosopher is doing nothing special compared to our original description of the problem. But the waiter, on the other hand, has fairly complicated code here. Well, there is some initialization that we need to do. So for the time being, ignore this statement, and let's see what happens in the do loop. In the do loop, again, we are looking at the code for the ith waiter. I is the index of the waiter. The ith waiter receives the hungry message from his corresponding philosopher. Having done that, he simply sets this Boolean true. And now, if it is the case, we are back to the loop again. If it is the case that the hungry Boolean is true, and you have the left fork, left from the perspective of this ith waiter, you have the left fork and the right fork, then we are in good shape. Right? So we could just send the E signal. Are you clear on this? And of course, as a result of this, the 2 forks that you are holding have become totally dirty. And so you set them to true. Now, it is the case that now the philosopher is eating, the ith philosopher associated with this. Note that all these variables declared above are local to each waiter, as before. I mean, nothing new there. Okay? So that is the easy case. The particular waiter happens to have 2 forks, and so he gives them conceptually to his philosopher in this sense, that he sends the eat message to the ith philosopher. Now let's see, what do we do if he is hungry, if your philosopher is hungry, but he does not, you, the waiter, do not have the left fork. So you need to acquire the left fork. So you send this message on needing the fork to your left neighbor, I minus 1, modulo whatever. Okay, the sum of minus is modulo. Okay? Now, as soon as you are doing that, you are claiming to have this. Is this correct? What must we be doing? We should be receiving messages from waiters, other waiters, which do the need, which accept the need pattern value. Right? And we are in anticipation that eventually, when that succeeds, when that operation succeeds, the bank operation succeeds, what is it that we got? Synchronous resonant pattern.
Someone else, right?
Someone else was willing to receive the input, right? We were outputting the need request. And if that need request matched with the corresponding need input in some other waiter, then we are through, right? So we have that fork, and similarly for the other one. So our weight, our need inputs are being received here. When you have the left fork, your philosopher is not eating, and the left fork is dirty. And this is where the policy that I described is being implemented. So you have your left fork. Your philosopher is not eating, but on the other hand, he has eaten with that left fork. So it is now dirty. At that point, you are willing to receive a request from your left neighbor. Okay. So that it is only under this situation would this input match with the corresponding output. The corresponding output will be from someone else to whom you are the right neighbor. Are you clear on this? This is the only difficult part in this. Let's start here. We are trying to understand when is it that the ith waiter will agree to receive this input need. I'm not sure where you're, if there's a confusion, where the confusion is. TSP notation or somewhere else. This need is a pattern value as before. There's no particular value being communicated. Pattern just matches. Right? Query is the input. And we are receiving input from, if we are 4, we are receiving input from 3. Okay, your left neighbor. Okay. So if you are receiving your input from your left neighbor, to him, you are the right neighbor. So this should be matching with somebody else doing I plus 1 bang need. Who would be that somebody else? The I number 3. Right? And when these two match, we have a left fork that is dirty, and our philosopher is not eating. So therefore, this waiter is willing to give it. And when you give it, it becomes the right fork of the waiter who receives it. Our left fork. It becomes the left neighbor's right fork. Okay? Conceptually, you clean it up and then okay. And given that you do not have your left fork anymore. And a similar thing for this. You have the right fork, and your philosopher is not eating, and is dirty, and in this case, you are willing to receive a read request from your right neighbor.
Are philosophers guaranteed to become hungry at some point?
Question was, are philosophers guaranteed to become hungry at some point? Implies that whether this thing terminates at all does not happen.
Then the solution, I'm going to posit that the solution is not starvation free. Assume that
Oh, you think that's not terminated it? You think?
for philosopher number one, let's say he never becomes hungry.
Well, at the beginning he does, as you can see from the loop.
Okay, so
Having eaten lunch, he may not become hungry.
Every philosopher becomes hungry at some point.
Initially. Right. As you can see from this loop. But having eaten lunch, they may never become hungry ever again. I think that should be okay. Yeah.
Okay, I have one question here as far as like in the write-up on it, it's talking about where if they have a dirty fork and nobody else wants it, they can continue to eat with that. So in the case where it says have L and not eating a dirty L, for instance, and it sends the query to waiter I-1, the need. Okay.
Over here.
Yeah, what actually, down below where it queries it.
Oh, sorry.
Okay, after the fork is dirty, stay on one more. Right there. Okay, what tells us that the waiter to the left doesn't need it and that it can go on and reuse the dirty fork?
So note that in our CST kind of notation, it is not the case that these three things being true, we are committed to this input.
It's not blocked.
No. Only, on the other hand, say that waiter, the corresponding waiter, is ready to do an output. That we will not be willing to receive unless the previous Boolean expression is true. Okay? And that is why we say that this input action is enabled when this is true.
But if there's
But it is enabled, but you are not committed to doing only this. In other words, having tested this, you are not quote-unquote blocked on this input. Having tested this, you are willing to do that input. But if that input for some reason doesn't happen, you have the option of the other non-deterministic fork. So eventually, the philosopher eats, and he said he sends it full, and obviously he then said he is full. Okay. Now, what is happening in the if statement at the top? Is it really the case, as I kind of said and then took back, that each waiter has exactly one fork? If we do that at the beginning, we won't be able to solve this problem. We could do that to as many waiters as possible, but we need to give to some waiter 2 forks to begin with. Okay. So to 3 waiters, you give 1 each. To a 4th one, you give 0. To a 5th one, you give 2. Because remember, you have a total of 5 forks only. And so to begin with, that philosopher whose waiter has 2 forks can actually use. And that is what is happening in initialization. Depending on the value of I. This asymmetry, this non-uniform code for all these waiters in this example is necessary. unless you have different codes for philosophers or somewhere else in the lasers. This is unavoidable. It's not a proof, but you can see that if you distributed force 1 each to all 5, then we could be back to a deadlock. Each of them trying to get the other one. They would all be trying to do, I need this one, for example. If all of them are trying to do that, then we are stuck. Now, this is a problem that we will also re-study this when we are doing the language called FR. So it's worth understanding this idea well. I think we have about half an hour, so I would like to move on to the main ideas of RPC then. And after the exam, I want to come back to more formal reasoning a little bit, the logic and limitations, curly brace something, etc. And I guess the next lecture is going to be question answer, is that right? You want that? And I would be happy to talk about Unix if you want that. But any other quick question answers are also okay. And if we run out of questions, then I'll proceed with this part. Okay, so far we have seen client servers being implemented without so-called procedure call mechanism. And now we are trying to do procedure call mechanism where the client and the server are not necessarily on the same machine. Okay? In other words, we want to be able to do the equivalent of calling a routine. And while the call is in progress, the control is in the routine. And eventually the routine finishes and returns back to the call. Now, we want to do this in such a way that the caller and the call routine may or may not be on the same machine. Okay? So we are not guaranteeing that the machine will be somewhere else, but we are saying that it is possible. So effectively, if you think of this whole thing as a client-server idea, again we have a loop, non-terminating kind of a process on the left box. The client, on the other hand, would conceptually make this procedure call P1, and we make this big assumption. And the assumption is that if you look at the arguments of this procedure, all the inputs to that procedure are in one place. All the outputs from that routine are in another place. And so the parameter passing mechanism that we are assuming here is that of call by value and call by result. Okay. If that is unclear, let me know and I'll explain this further. Now, that they are grouped together in the first few arguments, all the values, and the last few arguments are all the results, this is not significant. But then all the arguments are either call by value or result is. Okay. So, this procedure call that you may have in a typical language would then become, in our notation, a call to this RPC, remote procedure call server. It is remote because this server may or may not be on the same machine. Okay, so in general, we are pretending that it is remote. So to that remote procedure call server, we are sending the following things. We are sending the name of the routine, which in this case happens to be P1. We are sending P1 in this conceptualization as a name. This part of it is not in your book. And then we are sending values, V1, V2, etc. All the values. Having done that, this client will do a wait on the reply from the server. He expects to receive answers R1 up to whatever. So, from the client's perspective, you can hide these two send received. Are we clear on that idea? And so, it should be a system's responsibility to take that procedure call and turn it into a send message to a certain server and then wait for an answer from that particular server. Right? Conceptually, this one procedure call now became, in terms of CSP notation, a bang followed by a curve. And we want to be able to place RPCS, the server, on whatever machine we get. So this is the conceptual idea behind so-called remote procedure call. And unlike the previous discussion, we will be talking at a slightly more implementation level on this. Because the rest of the ideas are very much there in the next chapter in RPC in your book, but its implementation discussion is far too scarce in the book. Any question about the semantics of this? In particular, note that I did not put any 3 dots between the bang and the query. From the point of view of the client A, nothing else is happening between the bang and the query. In particular, this entire red box is not really being done by the client. So far as the client is concerned, he is doing a procedure call. But we have done something to the client's program. We being the system, operating system or whatever. We have done something to this procedure call so that effectively behind the scenes, we are doing a send to a particular server and a receive from the same server. Okay. Now, this assumption we won't get rid of until after 3 or 4 lectures down the road. The assumption being procedures are value parameters and result parameters. And there are no goals. Okay. So here is the architecture of a typical RPC system. And I will let you copy the slide. There's too much on it, so take it down. First of all, there are 2 machines here. May or may not be listed, but better to imagine that they are different machines. This is one machine. So the top box is one machine, the bottom box is another machine. Okay? And on the other hand, in terms of processes, not in terms of machines, but in terms of processes, we have 4 processes there. This is one process. This half where this dotted line is dividing the box is another process. And similarly, there are 2 in the bottom. Okay. These 2 processes are running on the so-called caller machine. This process and this one are running on the server machine. Okay. Yeah.
So we're saying that the client stubs are not actually part of the client program process.
You see that? Well, I'll refine my statement in a few minutes.
Okay.
As you know, there's always a bit of lying that is making wrong statements in any teaching. Initially, you say that, then you correct. Okay, so These are the activities that will happen in the order that their numbers are shown here. A client program, which is your process so far, right? Your process makes this local call. It simply thinks that this procedure is in fact in its own code. This procedure is called P1. So this is where a local call is made within your program. Are we clear on that? So, it is at that moment the control is here within this client program where I'm writing local call. Okay? But this local call, somebody had changed it into a call to another routine, not to your P1. But some other routine that somebody manufactured. And we'll see who that somebody is later on. Okay? So, instead of the actual call to procedure P1, what has taken place is another call to another routine, and that is step number 1. Okay? Are we clear on this? So instead of calling your P1, I call some other routine. Now, this other routine that you call, that is some massaging of this name P1 and the values V1, V2, V3, etc. Remember, these were the input arguments to the procedure P1. This massaging is called marshalling the arguments. It makes a large enough buffer of values out of these things. Put them all together in one place, and this packet is sent to the thing called RPC runtime. This is a process. These two are now communicating using, say, sockets or whatever. So, this item number 2 is indeed a send operation, whereas item number 1 was a procedure call. The only difference was, item 1, instead of doing your procedure call, did a different procedure call. But item 2 is indeed message passing. It is a send operation. It sends this entire package to this RPC runtime. Okay, RPC runtime is of course still on your machine, where the client is running. At this stage, the RPC runtime may not know where the server that you're requesting is located. So it has the job of finding somehow a specific server for you. Okay. So that is one of the main activities of RPC runtime. Somehow it should find a server. By that we mean, once it finds it, we mean it finds the name of this machine, as in an address, an internet address or an Ethernet address, whatever that uniquely identifies the server. Okay? So, somehow we find a server, and then we send this packet that we had received in item 2 there, we send that to the server. We attach extra material there. We say, this is coming from a machine named color machine, etc. So we give our own identity as part of that, and now we do step 3. Step 3 is being shown that way in thick arrows because this is, in general, a network transmission. Now we are leaving this machine, possibly going on to real cable or whatever, eventually arriving at the server machine. Okay? So even though we show, this is kind of misleading, even though I show these arrows as thick, it is these arrows which are narrow in bandwidth. These message sending, 3 and 8, are much slower compared to 2 and 9 because they are within the machine, they are much faster to send and receive. But once you are talking between machines, it is in general the case that they are orders of magnitude slower. In any case, so this package eventually arrives on the server's machine. And who receives this? The server's so-called RPC runtime process. So he receives this request packet. This server machine probably is hosting a bunch of servers, and it finds the corresponding server process. How does it know which server you are requesting? That part of it was coded up by the sender, by the caller's RPC runtime. So you find the appropriate process, and to that, item 4 here, to that you send the rest of the packet. Okay? And this server now reverses the way we packed together these arguments and the name of the routine P1 and actually makes what looks like a real procedure call and executes that. And that is known as dispatching. Okay? So what is it that this server better have? It better have the code for the body of the routine P1. Okay? So we are assuming that all such bodies of routines that you wish to call remotely are put together in this server. Dispatch is going to look like a big case statement, case on the name of the routine. If it is P1, jump to here. If it is P2, jump to there, etc. So that is your dispatch. You then execute the body of the corresponding routine. Eventually, you are done with that routine and you are returning from that routine. Right? And this return is your step number 6. In general, you are returning a number of results. So you package these results in essentially the same way as you did the argument. And so we marshal, we package them together again, and we send it to this process, the RPC runtime. The RPC runtime knows where to send these results to. Why? Because it was part of the package it received. Okay? So this package sent through the step number 8 arrives at the caller's machine eventually. Okay. And the caller's machine receives this packet, gives it to this box using message passing again, and that little box unmarshals, that is unpackages these results and gives them to this mod. And from there, you return as if you are returning from a local call. Are you clear on the various steps? Except for possibly find a server? Okay?
Marshalling of argument and results. Look, they both set up the same strategy.
They should. And they usually do. Even though there is no need to. As long as this marshalling the argument should of course reverse the unmarshalling here. And vice versa, similarly for this one. And because we need to be able to do this between any two machines, you generally accept a standardized way of marshalling and a standardized way of unmarshalling.
You mentioned when you were talking about the local call, when the local call is changed to something else, but still looks like a procedure call, you're saying.
Items 1 and 10 are local. Exactly, if you are imagining a specific instruction, item 1 is like a jump to subroutine machine instruction.
Even though it's another, you've got it.
Well, that is why I'm going to redefine my processes in a moment.
Okay.
But originally, this part is your user process. And this is one server process. Right? But conceptually now, after having done this, after we put together the RPC version, this program of yours, along with the ones that you are about to remotely call, becomes one process. For example, just for the sake of example, say you are doing some string operations in C, like string count, and crazy thing to do, but we put it on server. Okay? So what is it that we do? You obviously didn't write the string cat code for it. It's a standard library. So rather than link the standard library code of string cat, we link in your program another string cat routine, exactly same heading, everything. But the body of it is different. What does the body do? It takes the arguments that you give, does some massaging, and sends it to somewhere. Okay? So this is what we need to be able to do. Once you have indicated these routines are the ones that you may wish to call remotely, we need to manufacture some so-called stubs. These are stubs in the following. Exactly the same heading as the original routine. But the body of this routine is removed. Instead, we put a standardized body. What does the standardized body do? It does this marshalling at the beginning, and then sends. Then it awaits the reply. And when it gets the reply, it unmarshals the reply and returns. Okay. So that is the standardized body for any routine that you wish to call. And because it is so standardized, it should be possible for us to actually manufacture it through another tool. And you'll see that we'll do that later on. Okay. So, quite literally, your program, when it is running now as a user process, contains all of your code minus the bodies of the routines that you are going to call remotely, but the skeletons are still there. Those bodies are now replaced with bodies that will do marshalling and unmarshalling as required of the argument. And this is a standard process whose identity is known to the stubs that you have created. So they know which particular port to send this item number to. Okay? So we have no difficulty identifying the runtime process, the so-called RPC runtime process. On the other hand, RPC runtime process must somehow find a server that is willing to execute your P1. And of course, we are assuming that the server is already running. Now, how did we make the server up? We took all your routines that you are going to call remotely, such as P1, P2, etc. Remember, we gathered the bodies of all of these routines. We already have their headings. We compile and link all of these in a slightly special way. What is a special way? We add a dispatch at the top. This is simply going to look like this. You get the name of the routine. We'll change this part also later on. For now, imagine the name. You get the name of the routine, and based on that name of the routine, you have a switch state. If the name is P1, call the routine name to P1, which is now, remember, locally linked. Okay? So, once again, the entire server process is fairly easy to mechanically build, given the routines P1, P2, P3, etc. Are we clear on this? Right? Now then, what is the real difficulty of this? Well, one of them is finding a server. Where did you execute the server? What machine? That's one problem. But we postpone that. But on the other hand, the following is a real-life problem which is so frequent that we cannot ignore this. it is possible that the server machine dies, crashes. And depending on when it crashed, we could be doing serious damage to the whole thing. For example, suppose the server machine dies after having received this packet, after having unmarshaled this, after having dispatched, just before doing a return. Suppose it crashed. What do we do? Well, eventually the server, of course, is going to be rebooted, right? And this server process, as well as the server machine, are both up. What should the caller machine do? The caller machine does not know that this server has died. But even if it does know it has died, should we restart this computation or not? Should we start at the bottom of the routine P1 or should we start at the top? Remember that we crashed at the bottom of P1. The ideal thing to do is just start from there. But because it has crashed, we may not have a good record of that. On the other hand, if we start at the top, we may be doing some damage. As in, if this routine is add $10 to my account, you may do that 2 times instead of once. So these are the kinds of problems that an RPG system must deal with, along with finding the server. Now we can no longer assume that the server machine and the caller machines are so ideal that they will not crash at all. Because this is where the real difficulty is. If you assume that they are ideal, never crash, never run into any errors, what we have described here is solving the problem. But in the presence of this real life attack, this is not. We'll continue to
April 25th.